In this problem, we are going to find the Mohr circle for the given states of stress on the stress block. So we are asked to find what the principal stresses are, sigma 1 and sigma 2. We're asked to find what the max shear stress is going to be, and also what our principal angle is and our secondary angle is. So the first thing we want to do is we're going to want to find our coordinates to be able to plot our Mohr circle. So to start off with, I'm going to put a little note for what we denote as positive and negative. So as you can see on the right, I have our note. So for normal stress, if it's in tension, we denote it as positive. Compression is going to be negative. And for shear stress, if it causes a rotation that is going clockwise, we consider it positive. And if the shear stress causes a rotation in the counterclockwise direction, we denote that as negative. So now we can go ahead and find our coordinates for this stress block. So we'll start with our x-coordinate. And so for our x-coordinate, the first term is going to be our normal stress. So in our x direction, we do have a normal stress of 10 ksi, and since it's being pointed towards the stress block, it's going to be, that denotes compression. So our first term is going to be a negative 10. And then the second term in our stress block is going to be the shear stress also along that x face, and so it's going to be looking at this stress right here. And so since that stress is pointing down, it's causing a rotation of the stress block that is in the clockwise direction, so it is going to be a positive 5 ksi. Now when we look at our y-coordinate, in the y normal stresses, there's no force, or there's no stress being applied in the normal direction, so that's going to be 0. And then for the y-axis, we'll look at this guy right here. That stress is forcing a counterclockwise direction, so that means our shear stress is going to be a negative 5 ksi. And so now that we have our coordinates, we can plot those on our Mohr circle. So here is what our plotted Mohr circle looks like with our two axis points. So now the next step before we look at solving for what our principal stresses are going to be, we need to figure out what that center point is, like where it is on our Mohr circle. So to do that, I'm just going to denote that by calling it C. So our center, the equation for that is the average stress in our stress block, which is going to be equal to a negative 10, since that's the stress, the normal stress in our x point, plus 0, since we don't have any normal stress in our y point, all of that over 2. So that gives us a center that is going to be equal to a negative 5. So on our Mohr circle, I'm going to label that center. It's going to be at point negative 5 stress. Now the next thing we want to do is figure out what our radius is going to be. So our radius is going to be from the center to the points I'm looking at here. So we're going to take that length times that height. So this is going to be a length of 5, and this is also going to be a length of 5. So in order to find our radius, we just use the Pythagorean theorem. So our r squared is going to be equal to 5 squared plus 5 squared. So that leaves us that r is going to be equal to 7.07. Now that we have found those two, we can actually go ahead and solve for what our principal stresses are going to be. So the principal stress, our first principal stress is this point right here. I'm going to call that sigma 1. Our other principal stress is right here. This is called sigma 2. We're also interested in finding what the max shear stress is, which is going to be right here at tau max. It's going to be the top of our circle. And so to do that, so we'll start with sigma 1, our first principal stress. That is just going to be equal to the center coordinate plus whatever our radius is. So that's going to give us a value of 2.07. And then now if we go on to sigma 2, that is just going to be our center minus our radius. So that gives us a value of negative 12.07. And then lastly, our tau max, our maximum shear stress, that is just going to be equal to our radius, since it's the top of the circle, and so that's just going to be equal to 7.07. And then it should be noted that all of these values are all in units of KSI. Now the next thing for us to find is going to be our principal angle. So the principal angle is defined as being the angle it takes to rotate this point either to sigma 2 or all the way to sigma 1. So if we look at that in terms of angles, that means that if we're rotating counterclockwise, this is going to be our principal stress, or we can rotate it all the way down to sigma 1. So those are both going to give us principal stresses. Even though they might be different values, they're going to be in different directions, so it still gives us the same result in the end. And so on Morse circle, in comparing that to the actual stress block, we need to denote this as 2 theta p. So the amount it rotates on the Morse circle is actually twice as much as it rotates in the actual stress block. So I'm going to denote that as this also being 2 theta p. And so in order to start solving what that is, we first need to figure out this angle, what this angle is, just so it helps us figure out what theta p is. So I'm just going to denote that as a pink theta. So if we scroll down here, get us some more space, if we want to find what theta is, we can just look to the tangent of theta, and its height, you can see, is going to be a value of 5, so that's the opposite over adjacent, and the adjacent is also going to be a value of 5 if you just do that geometry. So that gives us a theta that's equal to 45 degrees. So if we look back and decide to move our x point all the way to sigma 1, so if we rotate through sigma 1, our equation for figuring out theta p becomes theta plus 2 theta p is just going to be equal to 180 degrees. So then if we plug in what we have for theta, we can solve for theta p, which then comes out to be 67.5 degrees clockwise, or you can denote that with an arrow. Now you can also, as we said, you can also rotate it down towards sigma 2. So if we're to do that, our equation then just changes to theta is going to be equal to 2 theta p. So then we solve for theta p, and that gives us a value of 22.5 degrees counterclockwise, or in that arrow direction. So although it looks like we get two different values, if you put them on the stress block, they actually end up being the exact same. They yield the same result. As you can see with the stress block on the right, when you either rotate it a counterclockwise direction of 22.5 degrees or a clockwise direction of 67.5, you get the same stress block, which looks like this. And then our stresses on that stress block, happen to be the principal stresses of sigma 1 and sigma 2. So now the last thing that we need to find is we need to find theta s, which is denoted as the distance or the angle to rotate from this point to our tau max. So if we denote that on here, it becomes 2 theta s. So if we go back and solve for that, we can say that if we're rotating to tau max, our equation just becomes theta plus 2 theta s is just going to be equal to 90 degrees. So similar to how we calculated the first one. So this gives us a theta s, which is going to be equal to 22.5 degrees clockwise. And then you can also solve this by rotating point x all the way to the other tau max or tau minimum. It would give you the same answer, but I'm not going to solve that in this case. So now I'm just going to go ahead and put these on a stress block. So here's what those stresses look like on the stress block when the stress block gets rotated counterclockwise 22.5 degrees. And in order to get those stresses on the stress block, you basically just take the coordinates of the rotation. So we rotated our point x right here to tau max. So our new line basically looks like this. So it's going from top to bottom. It's a little off kilter, sorry, but it means to be going through the center. So that means this is going to be our y prime and our x prime. And if you take those coordinates and put them on this stress block, this is what you'll get. And that's how you find all of the stresses and principal stresses and angles in this Mohr circle problem.